Hello, I welcome you to my presentation, a two-level approach for the crowd-based collection of vehicles from 3D point clouds. Next 10 minutes I will talk about crowdsourcing and paid crowdsourcing. I will show you the process chain of our approach, show you some result and conclude this presentation. So, crowdsourcing is a combination of the words crowd and outsourcing and describes the outsourcing of activities to unknown users via the internet. There are many crowdsourcing projects and many of them are based on the work of unpaid volunteers, such as Wikipedia and Zooniverse. So we know that also for the collection of geospatial data, here we call it volunteer geographical information, and the most popular project in that area is of course OpenStreetMap. So if we work with volunteers, we need an active community which is motivated to work at that project. And if we look at OpenStreetMap data, the main factors that users collect those data is that the contributions are free and that other users benefit from it in the shape of digital maps. This does not work for all applications. There are many tasks that could in principle be solved with crowdsourcing, but the bottleneck is finding enough volunteers. So we have to give other motivation, and the most important motivation here in that area is of course to pay money. And then we are in the area of paid crowdsourcing. If we have paid crowdsourcing, we take our tasks and publish them on online marketplaces which are responsible for the recruitment and the payment of the workers. So there are many of those marketplaces available, such as Microworkers or Amazon Mechanical Turks, and they have access to millions of registered crowdworkers. But there's a problem. If we have paid crowdsourcing, we know that the quality of the data can be very heterogeneous. Even so, most of the data that we get is of high quality. There will be always a significant amount of data with low quality. One solution for that problem is called the wisdom of the crowd. The idea is that we collect data not only once, but we collect it many times and then we integrate it and get at the end data of higher quality. So this is our workflow. What we want to do is to identify vehicles in 3D point cloud. So we start with the 3D point cloud. Then we calculate a 2D shading out of that point cloud and show that shading to the crowd. And the first task is to identify the coarse positions of the vehicles in that 2D shading. And then in the next step, we take these coarse positions, cut out small parts of the 3D point clouds, and then present the 3D point cloud to the crowd workers. And then the task of the crowd workers is to approximate all vehicles with 3D bounding boxes. Okay, we look at the first task where the crowd workers see a 2D shading and they have to identify the coarse positions. This is our test site, the Hessigheim dataset. It's laser scan data with a really high point density of more than 800 points per square meter. Here you see the 3D point cloud. We calculate this 2D shading out of the point cloud. Then in the next step, we eliminate all vegetation so that we see also the cars which are under the vegetation. And this is the graphical user interface for the crowd workers. Each crowd worker sees a strip of this 2D shading. He can navigate to the left and to the right. And the task is to identify all vehicles by clicking on the front and the rear of each vehicle. So if a crowd worker collects something wrong, he can of course delete the result and he can edit the positions in order to improve the results. And then we show that not only one time to a crowd worker, but each strip is shown to 10 crowd workers. And then at the end we get something like that. Each vehicle is represented several times in our results. So you see here the crowd data in yellow and the reference in red. And in the next step we integrate that. For the integration, we do not use the lines, but we use only the center point of the lines, which are represented here with dots in that image, and we use clustering algorithm, which is in our case DBSCAN, for clustering the data and for detecting the outliers. You see here the outliers are represented in red, all other data are represented in green, and the green data is then clustered, and each cluster has now a different color. And now we take the different representation of each cluster and calculate the average x and y coordinate, which we do here. And this is the result of the first step. So what is the quality? So we are not interested in the geometric quality at that point, because this is only a coarse identification of the car, but we are interested in the completeness and correctness. Here you see the comparison of the average over 10 data collections. So this is the data quality which we could expect if we collect the data only once. And you see what we will get if we collect the data 10 times, integrate it, and calculate the average. So if we collect it only once, we could expect a completeness of about 80%. After integration, we have a completeness of more than 93%. Also, correctness does improve, and therefore the quality improves significantly. So in the next step, we take those 2D coarse positions, cut small parts of the 3D point clouds, and now the crowd worker have to approximate each vehicle with a minimum bounding box. And here we see the graphical user interface for that. You see this is the minimum bounding box, and the crowd worker has to fit the data as good as possible to that car. So you can do that in this 2D projection or in the 3D data set as he likes, and he do that as good as possible. So, and then at the end we have something like that, and we do that again not only one time, but we do that 10 times and integrate these results. And this can be seen here. We use again a DBSCAN clustering algorithm. We see here the minimum bounding boxes if we look from top to the bottom, so in a 2D projection. You see the outliers in red, the remaining crowd data is represented in blue, and the integrated result, the average minimum bounding box, is represented in green. And now the question is, what is the geometric quality? So, for example, we can look at the position difference between crowd data and reference. On the left-hand side, we see the results before the integration. So if we would collect the data only one time, we get, for example, a position difference between 0 meters and 1 meters for about 65% of all cars. And the maximum position difference here is 6 meters. But if we collect it 10 times, integrate it, and average it, then we have position difference between 0 and 1 meter for 95% of all vehicles, and the maximum difference is here only 3 meters. You see here is a significant improvement. So, to conclude that, the problem of geospatial data collection by paid crowd workers is that very heterogeneous results are to be expected. If we collect the data several times, we can detect automatically outliers, and we can achieve a high degree of completeness and geometric quality. So here we achieve the completeness of 93.3% with the tenfold acquisition, and a geometric deviation of less than 1 meter for 95% of all collected vehicles. And we could even improve those values if we collect it not only 10 times but more times. So the average cost per vehicle are 8 cents for the coarse positioning, plus 42% for the approximation with the minimum bounding box, and this is for all 10 data collections. So the average total cost is 50 cents per vehicle. So, and in the end, we have something like that. We have here our 3D point cloud. You see all vehicles are here represented now with minimum bounding boxes. And this approach can be also adapted to other object classes, of course, very easily. And yeah, it's a very powerful approach, and you get data with high quality. This is what I wanted to show you in this presentation, and I thank you very much for your attention.